Good morning, everyone. Well, it's morning where I am. This is Professor McFarland, and I'm recording this in English with English slides, and I'm hoping that you can see the translated French slides for those of you who speak French better. I would like to go through the topic of pH and membranes and how that all works in a clinical setting. You've listened to some of my other recordings. These are designed to sort of fit into those recordings at a certain point. This will be early on in the other recordings that I've done. And now it's 5 years since I made those recordings, maybe 4 years. So a bit has changed for me. I probably have more gray in my beard. But I also think that the biochemistry that we're talking about, the biochemistry of the human body, has not really changed. And so what we're saying right here can fit into what I recorded before. And also, I will be around to answer your questions. So please write down any questions that you have so that you remember them when we can have a Q&A coming up. I'm going to record this lecture in several parts, and I'm not quite sure how the parts will be put together when you see them. But when you see them, just realize that remind me a little bit of what your question is about, maybe what slide it comes from or what image or term you have a question about. And that will help me to be able to find what we're talking about and answer your questions. Because we've got kind of two acts of translation to do here. We've got the translation from English to French, but we've also got the translation from the atomic world to the normal world, you know, from the chemistry world to the biology and medicine world. And so I'm going to be talking about the chemistry side of things. There are many things where we're going to try to make connections to the clinic, to the hospital, to the patient that you may be seeing at some point. But my main goal is to give you a good description of the atomic world that you're going to be looking through. And after that, then we can hopefully build those bridges to connect it to the clinic, to connect it to the patient that you'll be seeing. With all that in mind, building these bridges is going to take some work. And so I invite you to help build the bridges by writing down your questions, and I will be there to talk to you about those questions at some scheduled time frequently as you take this class. So that's why I'm actually excited to talk to you about pH and membranes, because it has a real impact on health. Some of this should be review from earlier classes that you've had. I'm not quite sure what you've had, so I'm going to try to review it fairly completely, and then I will deal with the Q&A. You'll have a quiz, and then you'll have a final on the topic. All of the quiz and final questions are going to be coming from these slides. So my goal right here is to be explaining the slides as best as I can verbally, understanding that it will have to be translated to French for some of you who are French speakers more than English speakers. So let's get into it. I will record this in parts, and the first part is going to be about pH. Why is pH important? And I'm figuring out exactly how my slides work. So there we have an advanced slide. And we're going to be talking about pH and membranes. Both of those actually have to do with the water molecule. Because human bodies are so much water, it's probably the most important single molecule to understand. And it affects how everything else works. So there's certain things about water that both affect pH and affect membranes. The two facts that we're going to go through: water is polar, so its chemical structure makes it polar. Therefore, it dissolves polar molecules, but it does not dissolve nonpolar molecules. This whole fact, this one little fact, actually sets up everything else. Also, because it's polar, and because its structure is made up of hydrogen as well as oxygen, you can have hydrogen interacting with it. And it turns out that it actually can bind another hydrogen and become H3O plus rather than H2O. Okay? So it binds protons, and the protons are little packets of charge. It's actually a really small thing physically, but chemically it's very important. And so you've no doubt talked about what protons can do, and we've talked about it in some contexts in the previous recordings that I made. So now we're going to talk about how those proton binding events can really change how water works. So it's very important to keep track of where the protons are and what they are doing. This is my basic assertion here. What I'm saying is that water is polar. So what that means is, hopefully you can see this video right here. It's just a little GIF that they are taking a charged rod. They take the rod and they sort of charge it up by rubbing it on something. Static electricity on the rod. And so they take the rod and they hold it next to a stream of 3 different liquids. You can see if you on this side, if you hold it next to hexane on the left, hexane doesn't change at all. But if you hold it next to water in the middle, water bends. The charge on the rod is enough to interact with the charges in water. This says that water must at least have some partial charge in it, and it reacts very differently than hexane. Isopropanol is on the right over here, and isopropanol will also bend. If you look at it carefully, it might not be bending quite as much as water. It might not be quite as polar. But the important thing is that water is bending in response to charge. Water is itself somehow partially charged. And so we want to start with this observation. We understand this observation by looking at its chemical structure. So water, of course, is H2O, 2 hydrogens and 1 oxygen. The thing about the oxygen in the middle is that not only is it binding 2 hydrogens, it also has 2 lone pairs on the back end of the molecule. If you look on the right side, you can see those lone pairs. Each of the lone pairs is made up of electrons, and so it actually has a negative charge associated with it. The negative charge is on one end of the molecule. Water is also, of course, bound to 2 protons. It's bound to 2 hydrogens. Each of those hydrogens is bound by electrons to the water, to the oxygen. But the oxygen is much more electronegative, so it's going to pull on those electrons. It's going to sort of keep the electrons close to itself. That means that the hydrogen is going to become partially positive because it's not going to win the tug of war. It's not going to win the pulling, pushing of the electrons. The oxygen is stronger when it comes to keeping the electrons. So the oxygen is more negative. The end with the lone pairs is more negative, but there's another end with the hydrogens that is more positive. This means that water has a dipole associated with it, an electric dipole with a positive end close to the hydrogens. This makes water act like a magnet. It has a small magnetic moment to it. It has a magnetic dipole because of this unequal sharing of oxygen with electrons. Oxygen will pull the electrons toward it. This is important. I'm taking a bit of time to talk about this because this sets up everything else. Water is a bunch of little magnets. Now the thing about those magnets is the magnets can interact with each other. You can have one magnet sticking to another magnet, right? And so the hydrogen atoms that are bound to the oxygen, they can actually have positive charge with them, and you can have the positive end of one water interacting with the negative end of another water. And it turns out that this interaction works really well when the positive of the hydrogen is lined up directly between the 2 negatives. That's what's shown right here. You have 2 negative oxygens, and between them is one of the hydrogens. It's bound by a covalent bond to one of the waters, the oxygen at the bottom. But it is bound by a weaker, longer, non-covalent bond to the oxygen at the top. So we can actually measure the strength of the bond by measuring the distance. The closer the two atoms are, the stronger the bond is between them. And so when you look right here, the hydrogen bond is twice as long as the covalent bond. That means very approximately it is about half the strength of the covalent bond. But covalent bonds are very strong. So that means that the hydrogen bond is still fairly strong. The hydrogen bond is weaker than a covalent bond, but is still strong enough to affect the behavior of the water. So any two water molecules can form this medium strength to high strength hydrogen bond between them. And this explains why water holds together. Water actually has strong intermolecular forces, strong forces between the molecules. It's because of this hydrogen bonding that water is even liquid under room temperature conditions. It is so small that it shouldn't be a liquid. If I look at it as a chemist, I'm looking at that water molecule and I'm saying it's so small it should just float away. It should be a gas. But water is actually so magnetic and it sticks to itself that it is able to stick to itself enough to hold it together and make it a liquid where the atoms, the different molecules, are able to move around each other, but they stay stuck to each other. They stay close. And so that's why we have the properties of a liquid. Water is like a magnetic liquid in one sense. It has a magnetic moment, a magnetic dipole associated with each molecule. Now, of course, if you take a magnet and you hold it up to water right next to it, you're not going to see anything happen. That's because water is like billions upon billions of tiny magnets, and they're all sticking to each other, and they're all sort of randomly oriented. So if you're stepping back from it, you don't see this magnetic part. But if you're right up next to it, and if you're the size of an atom, if you're very small, you can see this very clearly, or you can feel it in the strength of the bond that water will form. Okay, so after all that, that structure of water holds it together and is important for everything else we're talking about. The other thing about hydrogen bonding is you might notice that it's held together by an oxygen, a hydrogen, and another oxygen. Well, what if that other oxygen was on another atom? What if it was an alcohol? The bond would still work. All you need is two oxygens and one hydrogen. And what you have is so it would still work. Hydrogen bonding will work to any hydroxyl OH group. On the other end, so that will work by replacing the top part of the bond. You can replace the bottom part of the bond as well, and you would still have a hydrogen bond. The oxygen on the bottom could be an oxygen for a carbonyl. So actually I should say the oxygen on the top could be an oxygen on the carbonyl. The oxygen on the bottom could be a hydroxyl, anything that has a hydrogen bound. Basically, look at this slide, and anywhere you have a pattern like this of atoms, it doesn't matter what else the atoms are stuck to. Anytime you have a hydrogen between two oxygens, you have the ability to form a strong hydrogen bond. Hydrogen bonds can also be formed to nitrogens. Nitrogen is also electronegative enough to form the partial negative charge that you need to form a negative, the negative attractive force for the proton. And so you see right here, you can have the nitrogen also acting as a hydrogen bond acceptor or a hydrogen bond donor on the bottom. The donor is the atom that is covalently bound to the hydrogen, so it's giving the hydrogen to the hydrogen bond. The other one is accepting it. So you'll notice that there is pretty much any configuration you can come up with for organic chemistry that brings negative, positive, negative together. But you've noticed that there are no carbons here. You cannot hydrogen bond a carbon in any form, because carbon is not electronegative enough. This comes from its place on the periodic table. But carbon is just not able to form a negative that would actually attract a hydrogen. It cannot be a hydrogen acceptor or donor. It can only be oxygen and nitrogen for the common atoms in proteins. By the way, sulfur would also work in this case, although not quite as well as oxygen and nitrogen. So think about the arrangement that you have to form a hydrogen bond. Negative, positive, negative. It really matters whether the positive oxygen and the positive hydrogen, between the two oxygens, it really matters if that positive is between the two negatives exactly right. Because if it's not exactly between the two negatives, the attractive force between the three atoms will be reduced. So the strength of a hydrogen bond is very dependent on the direction of the three atoms forming the hydrogen bond. If you look at the hydrogen in the hydrogen bond right here, it's directly between, let me see if I can find my mouse. If you can see that, the hydrogen is directly between the two oxygens. That forms a strong hydrogen bond. If the hydrogen is held off of the line between the two oxygens, that means the plus minus plus arrangement is just not as good. It wants to pull it this way. It makes a weaker hydrogen bond because it's not lined up properly. Also think about this. Where are the lone pairs? For the example right here where you have the oxygen at the bottom, there will be two lone pairs on the oxygen, and they'll be pointing out at angles like this, okay? They'll be pointing out at 120-degree angles. So you can even say this angle, the POH angle, it should be 120 degrees because the oxygen has a lone pair. The lone pair thing may not matter as much to you, but it helps to explain what structures are. So if you can remember that from your general chemistry / organic chemistry experience. The other thing hydrogen bond really cares about, it is very dependent on distance. Optimal hydrogen bonds are 2 angstroms long. I like to use angstroms as length measures, although I should probably do it in terms of nanometers. Nanometer is 1 × 10 to the -9th meters, so nanometer. An angstrom, there are 10 angstroms in a nanometer. The reason why I like to use angstroms is because 1 angstrom is about the length of a typical covalent bond. You see right here, the NH bond is 1 angstrom long. So when we look at the hydrogen bond, the best hydrogen bond that you can get to the hydrogen acceptor will be about 2 angstroms long. Again, it's twice as long and about half as strong. But if you look at this right here, you have the 180-degree angle, the straight line arrangement between the donor bond and the acceptor atom, and you also have twice the length. The important thing about this is not even so much what it looks like, but that the hydrogen bond cares very much whether it can form this arrangement. If you have the positive charge of the proton moving around relative to the bond, if it's offline and if it doesn't have this geometry, then the hydrogen bond will be much weaker. Not just a little weaker, but a lot weaker. And in fact, hydrogen bonds have big effects. Whether you can form a good hydrogen bond gives you a lot of energy to the interaction, it makes the things stick together tightly, and it actually could be behind other phenomena that you can even observe. So if you take a bite into a bite of fruit, fructose is very sweet. I mean, we all know that. But there are different kinds of sugars that are less sweet. Glucose is actually less sweet than fructose if you do a gram for gram comparison. And mannose is actually even less sweet. If you take the powders and you taste them, you can test this to be true. So why is fructose so sweet? somebody looked at this and they tried to explain this for four different sugars right here. Fructose, F is for fructose, G is for glucose, M is for mannose, and T is for, I don't have it right here, but T is for, I think it's trehalose. It's some other sugar that starts with T. The thing about that is it is not very sweet. And what they did is they looked at how that sugar binds to the protein on the tongue that detects taste, the taste receptor in the tongue cells. The tongue cell receptor, we can actually get the structure of this and we can measure how long is the hydrogen bond. And you can see right here that the hydrogen bond of about 2 angstroms, remember that I said that about 2 angstroms is optimal. It turns out that the closer it is, the better it is. So if you can get a little closer than 2 angstroms, you can actually get a stronger bond. And when they looked at the structure, they found fructose makes the shortest hydrogen bond to the receptor. And here they have a graph measuring that right there. Fructose makes a 1.8 angstrom hydrogen bond. Glucose makes a slightly longer hydrogen bond. It's like 1.81 or something like that. Mannose makes a much longer hydrogen bond. It's 1.95 angstroms. And the T sugar makes a 2.4 angstrom hydrogen bond. If you look at this graph, you can hopefully see that they have sweetness going up and down. And so as sweetness goes up, the length of the bond gets shorter. That's what this graph shows. And so they're proposing that the longer the hydrogen bond, the weaker it is, and the less sweet the sugar is, just because it doesn't bind the protein tongue receptor as well. There's probably other things going on, but this is very interesting to me, that we can say if that sugar is very sweet, then we have a strong hydrogen bond being formed to it. So with that, I will actually cut off this particular part right now. We'll have this first one being about hydrogen bonds, and I will go and record the next one in just a second.